Excellent. I'm very happy to have Josh Alman from Columbia University here today to speak about generalizations of matrix multiplication can solve the light bulb problem. Stage is yours, Josh.
Thanks, Jeroen. Yeah, hi everyone. I'm sorry I couldn't be there in person, but I hope you're all having a good time in Montreal. And thanks to Jeroen and the organizers for letting me talk to you over Zoom. So I want to tell you today about an algorithm.
Josh, you missed dinner.
Most importantly, you missed the dinner.
Oh, yeah, I'm sure it was very good. Yeah, I love Montreal food and Quebec food, actually. I was particularly sad I couldn't come. Yeah, I know there's like a contentious opinion, but I'm a big fan of poutine, actually. Okay, anyway. So, I want to tell you today about this algorithmic problem called the light bulb problem, and how you can solve it using generalizations of the matrix multiplication tensor. So this is joint work with Hungji, who's a student here at Columbia. So my big picture goal that I want to tell you about is how to use tensors other than the matrix multiplication tensor to solve algorithm problems. So as you all know, there's been a lot of work that's gone into bounding the rank of matrix multiplication, lots of really nice ideas and lower bounds and upper bounds. And one of the main reasons that matrix multi has gotten so much attention is that matrix multi has a lot of different algorithmic applications. You know, in pretty much every area of computer science and computational science, you use matrix multi to speed up computations that you're doing. But what I want to talk about or work on, I guess, is finding other tensors other than matrix multi, and you know, the few other examples you were all familiar with, like polynomial multiplication, that also have algorithmic applications. So I think this is a rare situation in theoretical computer science, at least, where lots and lots of nice techniques have been developed for matrix multi, and they really haven't been applied to so many other, at least, algorithmic problems. Like usually when you have a nice new algorithmic technique, you can apply it all sorts of different places. And here, like the only sort of way we know to apply these is by reducing problems to matrix multi. Yeah, so the goal is that maybe some of these same techniques we've been developing over the years could lead to new algorithms for other types of problems. So in this talk, I want to tell you about like a first or maybe second step along these lines. So what I'm going to tell you about is a problem called the light bulb problem, where the current fastest algorithm for this problem uses matrix multiplication. And I'm going to show that actually you can replace matrix multiplication with other variants, which in particular can have lower rank than matrix multiplication, so they can be computed faster. So this is an example where you can replace matrix multi with something else that can be computed faster than matrix multi to try to speed up the algorithms for the problem. Okay, that's my goal. And the specific problem I'll tell you about today is of course the light bulb problem. So this is a problem introduced by Les Valiant in the 80s. And you know, Les Valiant like did a lot of foundational work on algebraic complexity, but he also did a lot of foundational work on like the theory of learning. And this was a problem he introduced in that context. So this is a problem that's like a basic primitive problem to capture the task of detecting or learning correlations among like random variables. So here's the problem. There's a parameter, which is some constant rho that you think of some positive constant, like 0.1 or 0.01 or something. So in this problem, you're given as input n vectors. There's n vectors that are -1, 1 vectors of dimension d. Unlike often in algorithmic problems where you're sort of assume you have like a worst case input, here the input is random. So all the n inputs vectors that you're given are uniformly random vectors, and they're all independent of each other, except that there's a planted pair that's correlated with correlation rho. So by that I mean their inner product is at least rho times the dimension. So two random vectors, their inner product is going to be like around square root of the dimension with good probability, but two of them have been planted to have correlation rho. And the goal in this problem, this planted pair is unknown to us, and our goal is to find the planted pair. So this is like the problem of given samples from n different random variables, find which pair of the variables are correlated with each. Yeah, so I'm going to, well, I have this box in the corner where I remind you what the problem is, but I think it's covered by my face, so I don't know if it'll be helpful or not.
Remove dots. Remove dots.
We do like previous talk where the faces like next to them. Or move them down. You've been moved out of the box.
Okay, thank you. Okay, so this is just a reminder that the input is n vectors that are all uniformly random, and they're all independent except for a planted correlated pair that we're trying to find. So this is a special case, as you can imagine, of a lot of problems in data analysis and in learning theory where like some part of the problem involves figuring out what's correlated among your inputs. And one thing that's interesting is that for a lot of these more general problems that the light bulb case problem is a special case of, actually the fastest known algorithm for these general problems comes from reducing it back to the light bulb problem. So just to give a couple examples, one is maybe you want to find correlations among vectors from some other range other than just -1, 1 vectors, like vectors of real numbers or points on the unit sphere or something like this. And in general, if your space has a so-called locality-sensitive hash function that I'll talk about later, you can actually reduce that problem to this just -1, 1 case and get basically the same running time. Another thing that is that in learning theory, there are a lot of nice problems, like if you've heard of these things like learning sparse parities with noise, or learning k-juntas with noise or without noise, which the light bulb problem is a special case of these things. And the fastest known algorithms for all these also come from reducing to the light bulb problem. So the light bulb problem can be used to solve a lot of different problems along these lines. Okay, and one thing I'll mention, actually, Les Valiant's initial motivation for introducing this was like an empirical study he'd been reading about, that humans seem to be able to solve this problem quickly. So there was like a real study they did where they lined up n light bulbs in front of a person, and then at every second they all turned on or off uniformly randomly, and they were all independent except for a pair of the light bulbs was correlated with whether they turned on or off. And humans seem to be able to look and pretty quickly detect which pair of the light bulbs were correlated with each other. So Les Valiant introduced this kind of to try to initiate an algorithmic study of like, why is it that people are able to do this so well? Okay, so that's why it's called the light bulb problem. So what do we know about it? How quickly can we solve it? So let me focus on the case when the dimension is like log n. It turns out, I'll talk about this more in a bit, it sort of doesn't, as long as the dimension is at least log n, it kind of doesn't matter how big the dimension. So there's basically two known approaches for this problem. One is based on locality-sensitive hashing, which is a very common technique for like nearest neighbor search types of problems. And the other is based on matrix multiplication. So first, there's like a straightforward algorithm runs in about n squared time, where you just, for each pair of the points, compute their inner product and see which one is closest. Okay. So using LSH, which is again a technique, this can be seen as a nearest neighbor search problem, because the correlated pair is going to be the closest pair of vectors in whatever norm you want. So using these types of techniques, you can solve it in time that's like n to the 2 minus order row. So like the best algorithm along these lines is by Dubiner and runs in time n to the 2 over row plus 1. So this is a sub-quadratic time algorithm for any constant row bigger than 0, but it's still, as row gets small, it still approaches quadratic time. So for small correlations, it still takes almost quadratic time to use these algorithms. But then in 2012, Greg Valiant gave like a breakthrough algorithm using matrix multiplication, which solves the problem in time n to the 1.6-ish, no matter how small the constant row is, as long as it's a positive constant. And a few years later, Karppa, Kaski, and Kohonen improved it to n to the 1.58, which is n to the 2/3 times the best current bound on omega. So our best, so this is the best known algorithm, and no matter how small row is, it still runs in truly subquadratic time. And these are like the two known approaches we have for this problem. So what I want to tell you about in this talk is a new algorithm that replaces the matrix multiplication in these matrix mult algorithms with other tensors. And I'll show you in particular how I'll show you about some really specific small tensors that you can use in this approach to beat Strassen's algorithm. So you could use this approach together with Strassen's algorithm to solve the problem. And I'll show you small tensors which can beat Strassen's algorithm by quite a bit. And another thing I want to tell you about is how you can combine locality-sensitive hashing with this tensor approach to give up improvements as rho grows. So like one property of the matrix mult algorithm is that you get the exact same time, no matter if rho is like 0.1 or 0.01 or 0.5 or whatever. Whereas LSH gets better as rho is improving. But I'll show you that with this new approach, you can actually combine them so that your algorithm actually gets better and better as rho is improving also. Okay.
Mention lower bounds yet or not? I don't remember.
We basically have no known lower bounds for this problem. Like the input size is n times d, and for all we know, you could solve it in time n times d. Yeah, so if omega is 2, like the best current algorithm would be n to the 4/3, which is not n times, not linear in n. So there's a gap there that basically it's big. Like we know very little about what's going on with this gap. Okay, so here's my plan for this talk. So I'm first going to start by defining properties of tensors that I'm going to need to state the result of how you can use a tensor other than matrix mult to solve this problem. And I'll introduce two new properties of tensors that we define. Then I'll actually state the result, how you can turn any tensor into a light bulb problem algorithm. Then I'll talk about some specific tensors of interest that you can plug into this framework and get algorithms from. And then at the end, depending on how much time there is, I'll actually give an overview of how these algorithms work, both the two prior ones based on LSH and matrix mult and how our new algorithm improves. Let's get started. So again, the new idea is to use generalizations of make tensors that still look kind of similar to matrix multiplication. So in particular, I'm going to focus today on tensors over the reals. Maybe things would work with complex numbers, but let's say the reals, whose inputs and outputs are formatted as Q by Q matrices. So they look like this, where I'm summing over 6 different indices, and there's 2 indices for the X variable and 2 indices for the Y variable and 2 indices for the Z variable, and my coefficients are real numbers. I'm saying inputs and outputs because I'm going to think of these tensors like this as bilinear maps, or you can think of it as T is representing the computational problem where you're given as input matrices X and Y, and your goal is for each of the Z variables to compute the coefficient of that Z variable. So for example, as you probably all know, matrix, like the Q by Q by Q matrix mult tensor is exactly of this form, where the coefficient is 1 if the I, J's, and K's are equal to each other and Z 0 otherwise, and then this bilinear problem is the same as the matrix mult. So I'm going to define 3 properties of such a tensor that are going to be relevant for our algorithm. The first is rank, that you are likely familiar with, and the second 2 are new ones that we introduced. So let's start with rank. So here's just the tensor again. So I'll go over this quickly. You're probably relatively familiar with it. So we think the tensor has rank 1 if you can write it like this, as a linear combination of the X's times a linear combination of the Y's times a linear combination of the Z's for the real coefficients. And then more generally, the rank of the tensor is the minimum M, such that you can write it as the sum of M different rank 1 tensors. Okay, and the intuition, of course, is that if a tensor has low rank, then that means the computational problem for T, or at least Kronecker powers of T, can be solved efficiently. So rank is going to be our stand-in for you can efficiently solve the corresponding bilinear problem. Okay. So the next one, which is a new notion, we call it efficacy. So when we define it, so here's the tensor again. So efficacy is meant to measure how closely the tensor is approximating matrix multiplication. So actually the name for it was kind of a light bulb pun. So you might know that like for a light bulb, its luminous efficacy is like the ratio of how much light it produces divided by how much power it consumes. So this is also going to be like a ratio of like how closely it computes matrix mults divided by how much noise it's introducing. Okay, so here's the definition. So first, for any particular I and j, so for any one output entry of matrix multiplication, I'm going to define the ij efficacy, which is a measure of how well it's computing the ij entry of matrix multiplication. And it's defined like this. So let me interpret this for you. So this is supposed to be like a ratio of the signal to the noise for this tensor T for computing the ij entry of matrix multiplication. So one thing you can see is that the numerator, this is the sum of the coefficients for all the terms that are supposed to show up in the ij entry of matrix mult. So like if this were actually the matrix mult tensor, this would be the sum of the q different coefficients that are 1 and that show up in the ij output entry. So this is the sum of the coefficients that are supposed to show up. So it's like the signal for computing matrix mult. The denominator is the L2 norm, so like the square root of the sum of the squares of all the terms which this tensor is including in the ij entry in the ij entry. So this is kind of measuring the noise because it's like it's measuring like all the different terms that are showing up, even the ones that are not supposed to be in matrix mult. This is the measure, and later in the talk I'll explain why exactly we did like a sum here and an L2 norm there. And then, so this is the efficacy for a particular ij output entry. And then for the whole tensor, its efficacy is the L2 norm of the vector of all its entry efficacies. So like just the sum over all the entries of the squares of the efficacies, the square root of that. So this is the measure of how well the tensor computes matrix mult. And when it comes up again, I'll like write this formula again to remind you. Okay, so that's the first tensor, and the second tensor is acceptability. So like our approach only works for certain tensors that we call acceptable tensors. So we say that this tensor T is acceptable if for each of its coefficients, either that coefficient is 0 or else, well, let me say it and then I'll explain what it means again, or else K is not equal to K prime, or else I and J are equal to I prime and J prime. Okay, so what does this mean? So in other words, if you look at a term like xik timesykj, so one of these terms, it's supposed to show up in the I comma j output entry of matrix multiplication. And we're saying this type of term can't mistakenly also appear in a different I prime comma j prime entry of matrix of this tensor. So if it appears with a non-zero coefficient and k is equal to k prime, so this is like a term that's really supposed to show up somewhere in matrix mult, then it has to show up in the right spot. So terms that are supposed to show up in one entry of matrix mult aren't allowed to show up in other entries of the tensor. And this is, I don't know, I actually don't have a great sense of how restrictive this is, but I'll talk about this a bit more later. Pretty much every tensor I know about that's been studied like as an intermediate in the study of these matrix mult algorithms does have this property. There's lots of like properties of tensor like tight and oblique and blah, blah, blah. And like all these different properties imply acceptability. So I think it's not super restrictive, but I'm honestly not so sure. Okay, well, let me tell you now our main result in terms of these notions. So our main result says this. So if you have any acceptable tensor T, then you can turn it into an algorithm which solves the light bulb problem in time n to the, I like to write omega sub L for the exponent of the matrix, the exponent of the light bulb problem, where the exponent is at most the log of the rank divided by the log of the efficacy. I'll show you in a second, like applying T is the matrix multi tensor itself achieves like a fairly low rank and a high efficacy, but sort of the goal is you could find other tensors where maybe the efficacy is not as big, but also the rank is smaller. And then this ratio of logs trade-off says it can help you to get a better algorithm. So let me now apply this to some tensors of interest, starting with the matrix mult tensor. Okay, so this is going to be a problem again for my picture on the side of the screen, I think. But here's this, and I have on the right a box which reminds you the definitions of efficacy and acceptability and so on. So just to remind you again, efficacy of the ij entry is a ratio of the sum of the entries that are supposed to appear in matrix multi divided by the L2 norm of all the entries that are appearing. The efficacy of the whole tensor is the L2 norm of the entry efficacies. It's acceptable if whenever the coefficient's non-zero, then either k is not k prime or ij is I prime j prime. And the bound you get at the end is the log of the rank over the log of the efficacy of the tensor. Okay, so let's start with the q by q by q matrix multi-tensor. So again, this is the coefficient is 1 if I is I prime, j is j prime, and k is k prime, and 0 otherwise. It's not hard to check that this is an acceptable tensor. It's kind of how we define acceptability. In particular, whenever it's non-zero, we just have this I equals I prime and j equals j prime condition. So it's acceptable for that reason. Its rank is about q to the omega by definition of the matrix multi-exponent omega. So let's compute its efficacies. So it's for a particular any entry ij, its efficacy is the same. The sum of the terms that are supposed to appear, there's q of them, which are with a coefficient of 1. So the numerator is q. And in the denominator, those are just the only terms that appear. So it's the square root of the sum of q1s. So the denominator is square root of q. So the efficacy for an entry is square root of q. Then the efficacy for the whole tensor is again the L2 norm of all these. There's q squared things we're summing over, and each their squared efficacy is q. So it's q to the 1.5. Okay, and then we plug it into our formula, and we see that the light bulb exponent is at most log of q to the omega divided by q to the 1.5, which is 2/3 omega. So plugging the matrix tensor into this theorem recovers the best known algorithm for the light bulb problem. Okay, and it's in fact in this situation our algorithm is pretty much identical to the current best known algorithm for the problem. Okay, so what I want to tell you about next, I want to focus not on big like q by q by q tensors, but on small 4 by 4 by 4 tensors, such as the 2 by 2 by 2 matrix multi-tensor. Honestly, the reason I'm focusing on small tensors is that this is the regime where I have the most interesting results to share about it. But also, I think it's a well-motivated setting since generally speaking, small tensors are like this are needed if you want your algorithm to be a practical algorithm. I know this is maybe this is a hot topic nowadays, but roughly speaking, like Strassen's algorithm is used in practice for matrix multi, and pretty much no other tensor-based algorithms are used in practice for matrix multi. So I'm going to focus on tensors that are as small as Strassen's tensor. Okay, so let me start just to make our bench line to compare to with the 2 by 2 by 2 matrix multi-tensor. So here it is, the tensor we all know and love. It has these 8 terms. It's acceptable just like before, all the calculations are the same as before. Its rank is 7 by Strassen's bound. Its entry-wise efficacies are the numerator or the 2 terms that are showing up in the z output, and the denominator is the square root of 2. So the entries efficacy are square root of 2. The total efficacy, just like before, is 2 to the 1.5. The exponent you get using it is log of 7 over log of 2 to the 1.5, which is 1.872. So this is our baseline that we're trying to beat using these 4 by 4 by 4 tensors. Okay, so let me start with one tensor, which is already able to beat this, which I call it a subset of matrix multi-tensor. So here is a tensor which consists of 7 out of the 8 terms of 2 by 2 matrix multi. So I've just removed the term x22, y22, z22. So this is still acceptable. Setting one of the coefficients to 0 does not change that it's acceptable. Its rank is 6 by, there's a nice identity by Winograd that's called the Strassen-Winograd identity that shows that actually the rank of this tensor is 6. And Winograd used it to make improve the constant factor of Strassen's algorithm. But then, because then you can add the 1 term to it and increase the rank by 1 and recover the fact that the rank of 2 by 2 matrix multi is 7. Okay, So what are the efficacies? So the three like outputs that we didn't change, their efficacies are still root 2, but this one that we did change, now its efficacy decreased. So it's now just the ratio of the one term divided by the one term, it's 1. So that because of this, the rank decreased, but the efficacy of one of the entries also decreased. So the efficacy for the whole tensor is the square root of 2 plus 2 plus 2 plus 1 now, which is square root of 7. And we get an exponent of the ratio of the logs is 1.841, which improves already on the 1.872 from Strassen. So we use this tensor, which is a bit less like matrix multi, but has lower enough rank that it actually gives an improvement for the problem. So let me now tell you like about a new tensor we introduced. We call it T2112, which is like sort of the 2112 is like describing the pattern of the efficacies of this tensor. So as a start, let me tell you, well, the starting point for defining this is matrix multi, but missing 2 of the terms. Okay, so here's 2 by 2 by 2 matrix multi, but I removed like one of the top right terms and one of the bottom left terms. Okay, so this is still an acceptable tensor. Its border rank is 5. So let me say, you might be familiar with like an identity by Bini, which shows like a tensor similar to this one as border rank 5. I'll talk about it in a second. This is actually like really a different tensor from that one. I'll talk more about that in a second. But we'll show, I'll actually show you in a few slides why this tensor has border rank 5. And we can calculate like its 2 diagonal entries that have the terms they're supposed to have efficacy root 2. Its 2 off diagonal entries just have 1 term, their efficacy is 1. So the efficacy of the whole tensor is square root of 6 now. And you get a bound of omega, like the light bulb exponent is at most log of 5 over log of root 6, which is 1.8 about, which improves even more on the previous one. Okay, so now, maybe some of you are unhappy with this because I claimed I was talking about small tensors in order to give like potentially practical algorithms, right? But here I used a border rank bound for this tensor, and as far as I know, like border rank bounds do not give good practical algorithms. Usually you have to take your tensor, raise it to a huge Kronecker power before you really get a rank bound, and then all hopes of practicality, fly out the window. But so here's what I'm gonna do. So when I say it has border rank 5, what that means is that you can introduce some formal variable called epsilon, and there's really some other terms that I'm hiding here. They're like epsilon times this term plus epsilon squared times that term or something like that. But there's other terms in this tensor that have coefficients of positive powers of some variable epsilon. And what I'm going to do is just, usually you sort of imagine taking epsilon to 0 or take some power to get rid of it. I'm going to just plug in some fixed value for this variable epsilon instead. So for any particular fixed positive number epsilon, this tensor actually has just rank 5 instead of border rank 5. And you can do all these other calculations, but like there's terms are going to show up in the denominator of the efficacy in terms of epsilon, but as they like subtract some like function of epsilon squared from the efficacies. But if you can just plug in a small enough like positive constant value of epsilon and still get more or less the same light bulb exponent by doing this. So in other words, I think the ability to like include junk terms, which like aren't supposed to be in matrix multi in this whole efficacy definition, allows you to fix small constant values of epsilon into these tensors instead of requiring you to take big Kronecker powers of your tensor. And you might imagine computational methods where you're like sort of trying to approximately bound the rank of your tensor, and oftentimes these things really only seem to be bounding the border rank, like they get close and close to your tensor but don't really achieve your tensor. And oftentimes you then have to figure out what's going on, how are these epsilons interacting with each other, blah, blah, blah. But here, the fact that you can get close enough to the tensor you want is already just enough to give an algorithm. And it saves a lot of work, like figuring out exactly how the border rank of your algorithm of your tensor is working.
And for the light bulb problem, you just work over the reals. You can always, your tensors are just over the reals, right?
Yep, exactly. Yeah, there's a nice question that is completely open, at least to me, of how to use tensors over other fields. But at least over reals, you can do exactly this. So let me briefly, for those who know about it, there's a nice paper by Bini in the 80s who showed that this other tensor, which has 6 of the 8 terms of matrix multi, has border rank 5. One thing you can check is that Bini's tensor really is different from our tensor. Like our tensor is missing like terms that are diagonally apart from each other, whereas this one's removes tensors that are in the same like column, terms that are in the same like column as each other. So they really are 2 different tensors. But I guess you could also like use this and get an algorithm out of it. But anyway, our new tensor has 2 advantages over this one. The first is that it's acceptable when you fix epsilon to be some constant bigger than 0. So Bini's tensor, like the terms that are hidden with coefficients of epsilon, some of them are actually not acceptable terms. So you wouldn't be able to just fix an epsilon like that. But our tensor, all the hidden terms are acceptable terms. And the second one is that something I'll talk about a bit later in the talk, that the pattern of the efficacies for our new tensor is better when you're combining it with LSH. I talked about this way to combine it with hashing to give faster algorithms. I'll talk more about that a bit later in the talk. So I want to tell you now, maybe this is a little bit of an aside, but I want to actually show you why this tensor has border rank 5, because it's kind of, at least for me, a rare situation where there's a tensor that's useful for something and where I actually have like a nice simple proof of why its border rank is what it is. And so, you know, if you take nothing else out of this talk and you hate the light bulb problem or whatever, maybe you'll at least appreciate this. So in some sense, this is giving a new, since this is 6 of the 8 terms of 2 by 2 matrix multi, this is in some sense giving another proof that 2 by 2 matrix multi has border rank 7. Okay, so here's the proof. So I'm going to start with this tensor. This is the tensor of the abelian group Z mod 2 squared, like the square of the cyclic group of order 2. So you can see in this tensor, all the indices like entry-wise add up to 0 mod 2. Okay, so it's the tensor for this group. And because it's the tensor of an abelian group, its rank equals the size of the group, which is 4. So this is a rank 4 tensor. This is our starting point. And what I'm first going to do is rename a couple of the variables. Okay, so bear with me 1 second. The first thing I'm going to do is rename the variable x01, like swap the labels x01 and x11. So all these that have x01 right now, I'm going to call them x11. And all these that have x11 right now, I'm going to call them x01. There you go. Okay. Yeah, and sort of the details of what I'm doing are probably not super important, but like the idea of what I'm doing is maybe what I want to get across. Okay, so I'm similarly going to swap the labels for x1 or for y10 and y11. So like this column of y's and this column of y's, I'm going to swap their labels. Okay, so far I've just renamed variables, so I've not changed the rank or anything. But the reason I did this is that now if you look at these 8 of the 16 terms, these are actually exactly the 2 by 2 by 2 matrix multiplication tensor. So like once I've renamed it like this, you can see 2 by 2 matrix multi shows up as a part of our tensor we're dealing with. But like that's not like enough for us. We need to somehow get rid of all these white terms that we don't really want. And I told you I'm aiming to get 6 of the 8 terms of matrix multi. So let me remove 2 of them. Like those ones are ones we're not going to bother with, but I really want to keep these remaining 6 orange terms here. Okay, so now what I'm going to do is something, I know different people have different names for this. I'd call this a monomial degeneration. So I'm going to multiply x, y, and z variables by powers of this formal variable epsilon, okay? And my goal is that at the end, all the orange terms are going to have a coefficient of epsilon to the 0, like a coefficient of 1, but all the white terms are going to have a coefficient of epsilon to some positive power. So that'll, like, as epsilon goes to 0, it'll get rid of all the junk terms we don't want. So let me do it for you. I don't promise I did a great job of like making it easy to see what's happening on the slides, but the details are not super important. So I'm first going to multiply x10 by 1 over epsilon. So I'm going to divide this row by epsilon. So I get this. And all these things, since I'm just multiplying like one of the variables, I'm not changing the rank of the tensor. Next, I'm also going to multiply x01, like the last row, by 1 over epsilon cubed. Okay, so I've rescaled some of the x variables. Now I'm going to rescale some y variables. So I'm going to multiply y11, like the third column, by 1 over epsilon, like this. Okay, so like this one is epsilon to the -4 now, because it got -3 from its row and -1 from its column. I'm also going to multiply y00, like the first column, by 1 over epsilon cubed. There you go. And now I'm going to multiply the z variables by positive powers of epsilon. So I'm going to multiply z00 by epsilon cubed, so that like this orange term we want to keep is going to have a coefficient of 1, and this orange term we want to keep is going to have a coefficient of 1. So there you go. I multiplied like the 4 terms of z00 by epsilon cubed. So I'm similarly going to multiply z01 by epsilon to the 4 so that I can keep this term here. Okay. I'm going to multiply z10 by epsilon to the 4 so that I can keep this term here. And I'm going to multiply z11 by epsilon so that I can keep this term, and there you go. Okay, so the details maybe not super important, but I just multiplied all different variables by different powers of epsilon. And what you can see now is all the orange terms I want to keep really have a coefficient of 1. And almost all the white terms that I want to get rid of have positive powers of this variable epsilon as their exponents. And that's true for every term except this pesky bottom left term with a coefficient of epsilon to the -5. So the last thing I'm going to do is I'm going to do a rank 1 update to remove that term. So the current tensor has rank 4. So if I just delete one of the terms, the resulting tensor has rank at most 5. Deleting one term changes the rank by at most 1. So now I have a rank 5 tensor where all the orange terms have coefficient of 1 and all the white terms have coefficient of some positive power of epsilon. So this shows that the orange terms have border rank 5, but what I'm really doing is plugging particular small constants in for epsilon into this whole thing, and then getting a particular tensor with rank 5 that we use. And you can see it's acceptable. Actually, more generally, if you like start with any tensor of any group, any finite group, and do stuff like this, you'll always get to an acceptable tensor. So you don't have to worry about acceptability when doing like monomial degenerations like this. Okay, yeah, that's just, I thought a cool thing that you can actually get to this by starting with a group tensor and doing simple operations to it. So just to summarize where we're at so far. So what I showed is that if you restrict to rank bounds on these 4x4x4 tensors, we can improve the exponent from like 1.87 that you get from Strassen's algorithm to like 1.79 that you get from this new tensor I just told you about. And one thing we did do, or really Hangji, who's much better at coding than I am, did, is confirmed by some like optimization software that this actually is the best like exponent you can get using a tensor of size 4x4x4. So I think it's kind of, I kind of expected the best tensor to be like some crazy thing that would come out of optimization software and would be hard to understand. I was like pleasantly surprised that actually this relatively nice tensor is able to get the best possible bound for these small tensors like this. And okay, for bigger tensors, we can recover the best bound that's 2/3 omega for the exponent. And I don't know how to improve this yet, but I think it would be, I'm optimistic that it's possible. And one thing I just wanted to mention, I think I talked about this a bit before, is that tensors, other than matrix multensors that are acceptable, really do arise in a lot of situations that you all might be familiar with. Like the subset of matrix multensors is one example that I'll mention this on a later slide, but there's work by like Kohonen and Alman and Karski and Karppa on showing that these can be used for Boolean matrix multiplication. So these types of tensors really have been studied before. Also, structured tensors of finite groups always are acceptable tensors. And there's lots of things like free tensors and tight tensors and oblique tensors, which all these definitions imply your tensor is acceptable. Another situation I think is kind of exciting is if you're familiar with the laser method, which is the way we get our current best bounds on omega, there's like intermediate tensors that appear in the middle of this laser method, which really do look like matrix tensors plus a lot of like other junk terms. And in the laser method, there really is a step where you like kind of lose something because you have to get rid of these junk terms. But maybe like they could somehow be used as an acceptable tensor, and these junk terms are relating to the efficacy and so on. Yeah, and I don't know. We've tried this a little bit and haven't had success, but I'm optimistic that like there's a lot of different ways to try to come up with tensors like this. So please help us find tensors that beat 1.582 for this light bulb problem. Yeah, think about your favorite tensors and if they're helpful here or not. So I want to move on now to the like last part of the talk, where I'll actually give you an overview of how all these algorithms for the light bulb problem work. So this is my transition from mostly talking about tensors to mostly talking about algorithms. So here's my plan. So I'm going to first talk about the previous approaches. I'll tell you about LSH, what that is and how we use it. And I'll tell you about how you solved it with matrix mult. And then I'll tell you about our new approach using other tensors and how it can combine with LSH also. Let's start with LSH, which is maybe like the simplest approach for solving this problem, which has been known for quite some time. Here in the box again is just a reminder of what the problem is. So there's a constant row that's a positive constant row. You're given as input n vectors that are dimension d, and they're all uniformly random. Sorry, they're all uniformly random, and they're all independent except for a planted correlated pair with correlation rho. And your goal is to find the planted pair. Okay, so what is locality-sensitive hashing? For some parameter k, I'm going to think of k as for now, to just be simple about it, as close to n. I'm going to pick a random hash function that maps like vectors of length d to one of k different buckets. Okay, and I'm going to want my random hash function to have two properties. The first is that the function should map uniform random points to uniform random buckets. So like if you hash a bunch of uniform random points, they like get evenly distributed across the buckets. And the second is that I want the hash function to be more likely to map correlated vectors to the same bucket as each other. So I want it to map points to buckets so that the correlated pair is more likely than a random pair to be mapped to the same bucket as each other. So if I have a hash function like this is at a high level what a locality-sensitive hash function is. If I have a function like this, then the algorithm you get out of it is you just start by hashing all the inputs into buckets, and then you compare all the pairs of points that have been hashed to the same bucket and check if they're correlated or not. Okay, and the idea is that, you know, if you set up exactly what these properties mean appropriately, maybe there's like at most like a linear number of hash collisions, so like pairs of vectors that really hash to the same bucket as each other. So you do like a linear number of actual comparisons of vectors. So the running time of this algorithm is n. So it's like a linear time algorithm, but it only has like a low success probability. It's only going to work if the correlated pairs were mapped to the same bucket. So what you have to do is repeat independently many times, so that like one with good probability, like at least one of the times the correlated pair actually does get mapped to the same bucket as each other, and you'll find them. So let me like show you like the simplest example of a function, like a hash function like this. It's called bit sampling locality-sensitive hash function. So we're going to define just the hash function by so let me write little k is log base 2 of big K, log of the number of buckets we want. And then I'm going to just pick little k different independent coordinates from the d dimensions, and I'm going to project vectors onto those little k coordinates. Okay, so I'm going to the hash of a vector x is just going to be the projection onto those k random coordinates I picked. So there's 2 to the little k, which is big K different outputs of the hash function, different buckets. And let's check this really has the properties I said it does. Well, first you can see a uniform random x really is mapped to a uniform random bucket because its projection is still uniform random. And the second thing you can check is that if you have a correlated pair of vectors with correlation rho, then the probability they're mapped to the same bucket is like this. Like in each of the k coordinates, there's a 1 plus rho over 2 probability they have the same value in that coordinate as opposed to just a half. So this probability is like substantially bigger than a half to the k. So it's substantially bigger than 1 over k. So the total running time you'll get is like order n for each hash function, and then you have to repeat like 1 over p times to get a good success probability. And if 1 over p is like much bigger than 1 over n, then the running time of your algorithm is much smaller than quadratic. That's the idea. You know, there's some calculations that I'm intentionally omitting, but because like as rho goes to 0, this probability here really goes to a half, and p really becomes like 1 over n. This running time approaches quadratic as rho goes to 0. And there actually are better LSH functions for this task than just bit sampling. There's like a nice paper by Dubiner where he gives a more complicated function that's able to beat this. Okay, that's the LSH approach. So let me tell you now about the matrix multiplication approach. So here's like idea 0, like for how to use matrix multi to solve this problem. This like the most straightforward idea, and it's not going to be fast enough. So we're going to start by just forming the n by d matrix of all these input vectors. So the input, remember, is n vectors of dimension d. I'm going to put them next to each other into an n by d matrix. Maybe there's a d by n matrix. Okay, I'm going to put them next to each other into a matrix, and then compute the product x times x transpose. Sorry, I think this is x transpose rather than x. Okay, so I compute the product x by x transpose. Why is this a good idea? Well, the ij entry of this product is just like exactly the inner product, or gives you the correlation between xi and xj. So in this product, we just want to look for the biggest value, and that will solve the light bulb problem correctly. Okay, the issue with trying to use this to solve the problem fast is that this output matrix Z is an n by n matrix, which has n squared entries. So no matter how fast your fast matrix multiplication algorithm is, it's still going to take quadratic time to do this matrix product and output n squared numbers. So if we want to get a sub-quadratic time algorithm, we have to do something more clever than this. So here's what we do. This is like the main idea that Greg Valiant introduced. So let me start by making the dimension a bit bigger. Like before I was talking about dimensions log n, I'm actually going to focus on a much bigger dimension that's like some constant times n to the 2/3. Okay. And one nice thing in this prior work that I don't want to talk about pretty much at all is that there are nice tools that increase the dimension from smaller d to larger d without losing too much in the correlation. So using these tools that I'm not going to talk about, you can sort of, without loss of generality, assume the dimension really is like n to the 2/3. So here's what we're going to do. I'm going to start by partitioning up the n different input vectors into n to the 2/3 groups of size n to the 1/3 each. Okay. And for each group, I'm going to make a single vector. So for each group L, I'll make a single vector x tilde L, which is just the sum of all the vectors that have been put into that group. And the idea here is that if two groups don't have the correlated pair, then they're both just sums of independent random vectors, and they're also sort of independent random vectors. If two groups contain the correlated pair, then there's still a little bit of correlation because the correlated pair have been added to those groups. And we're going to look for that like smaller correlation from among the groups. Okay, so the algorithm is, again, we're going to form the like n to the 2/3 by n to the 2/3 matrix, which you get by concatenating just all these group vectors, and then compute that times its transpose. Okay, and this really, now because we're multiplying two n to the 2/3 by n to the 2/3 matrices, the running time is n to the 2/3 omega. So this is how you can really hope for a subquadratic time algorithm, because we're making these smaller matrices that we're multiplying. But the big claim that I haven't shown you yet is that from this new matrix Z, you can still detect which groups the correlated pair are in. And once you know which groups they're in, you can recurse or even just like do some brute force to actually find the correlated pair. So let me give a one-side explanation of this claim. So here's the claim again, that from the value of the inner product of the group vectors, you can determine whether or not the correlated pair is in these groups. So here's what the inner product of the group vectors looks like. It's just the sum over the inner product of the sum over everything in the ith group and the sum over everything in the jth group. So it's the sum over all the pairs of vectors of their inner product. Okay, so what does this thing look like? Well, it looks like a sum of n to the 2/3 inner products. Here I'm summing over two different things of size n to the 1/3. So it's the sum of n to the 2/3 inner products of random -1, 1 vectors whose length is some constant times n to the 2/3. Okay, so let's figure out what happens with this random variable when the correlated pair is or is not in these pair of groups. So if it is not in the pair of groups, so if these groups are just actually all independent random variables from each other, then this inner product is a sum of like n to the 4/3 random -1, 1 values. It's a sum of n to the 2/3 inner products of length n to the 2/3. So in total, it's n to the 4/3 things that you're adding together. They're not exactly independent of each other, but they are at least pairwise independent of each other. You can convince yourself of that if you think about it a bit. So we can still analyze the variance and the standard deviation of this random variable to figure out how it's distributed. And one thing you can calculate, so it has mean 0 because it's a sum of a bunch of things with mean 0. And its standard deviation is just like the square root of the number of things you're adding up. So its standard deviation is like n to the 2/3. Okay, so then we'll apply like Chebyshev inequality and say that means its inner product is at most some constant times n to the 2/3 with good probability, like probability 2/3, let's say. Okay, so that's what happens when the correlated pair is not in this pair of groups. I want to say the inner product is small with good probability. So case 2, the correlated pair is in this pair of groups. So now the inner product is distributed like before, but also plus the inner product of the actual correlated pair of vectors. So now its standard deviation is the same as before, but instead of having mean 0, now its mean is coming from the correlation of the correlated pair. So the correlated pair, since they have correlation rho, their inner product is like rho times the dimension. The dimension is this, like 100 over rho squared times n to the 2/3. So the mean is that times rho, which is like 100 over rho times n to the 2/3. So by Chebyshev inequality again, that means this inner product is going to be bigger than like 50 over rho times n to the 2/3 with good probability. So to summarize, if the correlated pair is not in the pairs of groups, then the inner product will be small with good probability. And if it is in the pair of groups, the inner product will be big with good probability. So the algorithm just repeats like log n times and sees which pair of groups has a big enough inner product most often. And that's where the correlated pair has to be. That's how you get this n to the 2/3 omega running time. Okay, so let me tell you our sketch of how we do our new algorithm. So the idea is the same as this matrix mult algorithm I just showed you, but we're going to use the new tensor T instead of matrix mult. So we're going to start just like before. We'll partition up the inputs into D groups of size n over D each, and we'll add up the vectors together in the same group and concatenate these vectors to form a D by D matrix x tilde. And then we'll like multiply x tilde times x tilde transpose, but rather than like do the matrix product, I'm really gonna plug them into the bilinear problem defined by our tensor T or Kronecker powers of our tensor T and evaluate that and find the output of that bilinear problem. And like before, the idea is that this is going to be faster than matrix mult, so it should give us a faster algorithm, but it's less accurate than matrix mult if we didn't pick the matrix mult tensor. Let me do like so entry ij of the result now is going to be this. Let me just repeat it on the next slide. So here's what we're outputting in entry ij of the result now. It's in terms of the coefficients of our tensor. Let me quickly show you. We can still do the same kind of two-case analysis as before, where we analyze the mean and the standard deviation of what this sum looks like. Okay, so if the correlated pair is not in this pair of groups, now like each of these terms is still like a sum of random -1, 1 values before, but they're being multiplied by these coefficients of the tensor. So the ij entry, it still has means 0, but its standard deviation is now this, where the standard deviation is now like multiplied by like the L2 norm of the squares of the coefficients. And like this L2 norm is coming up just exactly because variance is like the expected value of, it involves like expected value of the square of the appropriate thing. And then to get standard deviation, you take a square root of that. Okay, so when you do the calculation, this is what the standard deviation of the entry is. And in the case when the correlated pair is in this pair of groups, it's the same standard deviation as before, but now the mean, instead of being rho times the length of the vectors, is scaled by the coefficients that are like showing up that are supposed to be there in matrix multiplication. So the mean gets multiplied by these alpha coefficients now that we're using this new tensor. So to distinguish the two cases, just like before, we roughly speaking need the mean to be more than the standard deviation. So when you take the ratio of these, this is exactly saying that the ij efficacy of the tensor is big enough. Like the ratio of this is like the numerator of what was in the efficacy definition, and this is the denominator of what was in the efficacy definition. To summarize, if the correlated pair are put into groups gi and gj, then we can detect them as long as the ij efficacy of our tensor is big enough. So like you can think like the probability of success is roughly the probability that when you put them into random groups I and j, that the ij efficacy is big enough. And there's some kind of trade-off where like as you increase d, like this increases the probability because you're like trying to beat a smaller amount for the efficacy, but it also increases the running time because you have to take like the Kronecker power of the tensor, you have to take scales with like the log of the d. So there's some trade-off where you find the optimal d and then do this and solve the problem. And the reason, even though this looks like some kind of threshold thing about the efficacies, really the L2 norm of all the efficacies ends up showing up when you look at what the efficacies of the entries in the Kronecker power of your original tensor are. Like this L2 norm ends up showing up when you optimize this in the Kronecker power of your tensor t. Okay. Yeah. So let me, how much time do I have left? Do I have any time left?
Yeah, like 2 minutes. We started a bit late. 2 or 3.
Okay. So let me very quickly tell you about combining this with hashing. I think this is cool. So in the algorithm I just showed you, we partitioned the inputs up into groups, but we just did it completely arbitrarily or randomly. And then what we saw is that if the correlated pair are put into groups I and j, then we'll detect them as long as the ij efficacy of our tensor is big enough. So what I'm gonna modify this by, instead of putting them into arbitrary or random groups, I'm gonna partition them into groups according to a locality-sensitive hashing function. So I'll pick some function h, like the bit sampling one that we did before, and put input xi into the group whose index is the hash of xi. So what do we get out of this? Like still like before, all the uniformly random independent vectors go to random buckets, but now the correlated pair is likely to be put into a pair of buckets whose indices are correlated with each other. Okay, so if we could have a tensor where the ij efficacy is correlated or is like larger whenever I and j themselves are correlated with each other, then we can take advantage of this to get a speed up. Like we'll be putting the correlated pair into a bucket with higher efficacy than a random bucket, and we can get a faster algorithm out of that. So here's the slide where I showed you the tensor T2112 before, and in particular, it has exactly this kind of property we want. That like the diagonal entries have larger efficacy than the off diagonal entries. So just writing that again, let me slightly renaming things, like the 2 diagonal efficacies are like √2, and the 2 off diagonal efficacies are like 1. So then when you take a Kronecker power and you have indices, which are vectors of length m, like the efficacy of a bucket is going to be root 2 to the d plus the inner product between I and j. Like you pick up a root 2 whenever they're like maybe over 2, something like that. So you pick up a root 2 whenever the entries are the same as each other, and you just pick up a 1 whenever they're different from each other. So in particular, if we use bit sampling LSH to put them into buckets, then a random pair of vectors will still be mapped into buckets with whose efficacy is about root 2 to the d, but the correlated pair will be put into buckets where the efficacy is like 1 plus rho to the root 2 to the 1 plus rho d. So like the correlated pair gets put into buckets with higher efficacy, and then you can use that to say we don't need to repeat as many times, and or you don't need to make d as big, and you get a better running time. So here's just a graph. I'll talk about it very, very quickly. That normally there's like a green line showing the running time of the matrix mult-based algorithm. By using this, you now get a new algorithm which gets better and better as rho goes, and like you're mapping the correlated pair to entries with bigger efficacy. And then there's another approach, like just using LSH, that starts off worse but gets better as rho gets larger. Okay, so very last slide. What's next here? So first of all, I think it would be very exciting to find better tensor to asymptotically speed up the light bulb problem, and I hope you all can help us with this task. But also more generally, I think it's really interesting to try to find other algorithmic problems that can be solved using tensors other than the matrix mult tensor. So potentially, like following along these lines, maybe there are other applications where, like the light bulb problem, where currently we're using exact matrix mult to do it, but really we only need some kind of approximate matrix mult, and this could lead to improvements. And I mentioned this before, but there really are other tensors that are known to be useful for Boolean matrix mult, like Kohonen and showed that tensors with the same support as matrix mult can be used, and Karppa and Kaski and more recently Harris have shown that these subset of matrix mult tensors can also be used in that context. But also, more generally, it would be neat to find problems that can be solved with tensors that are nothing like matrix mult or the other tensors we usually study. Okay, that's it. Yeah, thanks.
Questions?
I have a question back to the Bini tensor.
Oh, yeah. Do you want me to? I can try to put it on the slide again.
So you said that there's no better tensor than that for, certain point you wrote that computation, so that there's no better tensor in size 4 times 4 times 4.
Yep, that's right.
Yeah, and then you also showed us that it has border rank 5. So, the Bini tensor is very peculiar also from the geometric point of view. It's, for example, it's one of the first example that you use to show that there exists tensor whose border rank is smaller than the cactus rank.
Yeah.
So it's a very peculiar one, and the same phenomenon, the same pattern applies if you look at the symmetrized version of the Bini tensor. So it has the same peculiarity. So I was wondering, since you are asking for helping you to finding better tensor than that, so should I look among those tensors of high border rank with some special property like this, or where should I look for better tensors?
Yeah, so the short answer is I honestly don't know where to look for the best tensors. What you're aiming for, you really want tensors with low border rank, not high border rank, right? But because you at the end get this ratio of the rank or border rank divided by the efficacy. So you want tensors that are somehow similar to matrix multiplication, but still have low border rank. I do think, yeah, these examples indicate that tensors that are kind of like these are probably good ones to look at. The short answer is I really don't know what tensors, beyond like the trivial answer of, you want tensors where these quantities are big. I'm not so sure what else to say.
Okay.
Yes, Josh, just wanted to point out, I think this tensor I think Peter Vana had analyzed this tensor some time ago.
Oh, great.
I don't know if this is somehow published or not, or just some notes. I just asked him, maybe he can send it to me.
Oh,
Some years back.
oh, thanks. Yeah, if
Cool, you like the beanie. The beanie is my favorite, has always been my favorite tensor.
yeah, it's a nice one.
This is really
Oh, if you or he could send that to me, that'd be really great.
yeah, I'll ask. Yeah.
So Lensberg and others have these nice geometric interpretations of tight tensors and other varieties of tensors. Is there a nice geometric interpretation of acceptable tensors?
Mhm. Oh, I'm sorry. I think I missed the end of what your question
Is there a
was.
nice geometric interpretation of acceptable tensors?
Oh, yeah, I'm really not sure. I mean, I guess at least Hangji and I, we've been focusing on tensors that like types of acceptable tensors, like tight tensors, which do have better descriptions. Yeah, I'm not sure. It's kind of a weird definition. I'm not that confident how like specific it is to the light bulb problem or how natural it is. Yeah, I'm really not sure.
Thanks.
Because Jam would complain it's space dependent.
Yeah, but you could still say, what do tensors look like? That in some ways it look like.
Yeah.
And so is there a nice?
Yeah. And I was wondering this bordering 5 construction that you have, right? So
Yeah.
can you also use it to show that all 4x4x4 tensors have bordering at most 7, which is also true, right?
Sorry, to the which tensors?
So you can use it to reprove that Maze multiplication has bordering 7, right?
Yeah.
But can you also use it to prove that all 4x4 tensors, 4x4x4 tensors have bordering 7? That's also true. That's also
Yeah.
that work as well. What do you think about it?
That's a great question.
So you have this big support. So there's a lot of
Yeah. Off the top of my head, I'm not sure, but I think that's quite plausible. Yeah, there's enough degrees of freedom to multiply around by all the coefficients you need that I think it would work.
And does it generalize at all if you used what did you use, C4 C multiplicity to the power 2, right?
Yeah. I don't know. We've tried and have not found any exciting generalizations of it. Like we stared at C4 and we stared at C2 cubed and C2 to the 4 and like it's yeah. I don't know. I think there must be some exciting generalization, but I'm not sure what it is.
Thanks.
Yeah, there's like as you know, there's lots of people in the world who really try to use these group tensors to say things about matrix multiplication. So they might know better than me what exactly you can show with them.
But this construction was I haven't seen it again.
Yeah, it's nice how simple it is.
Yeah. Anything else? Question? No? All right. Thanks, George.
Thanks, everyone.